So in this lab today, which by the way, I am on Zoom right now and not on, I'm not on Microsoft Teams because it's just me today. We're looking at Bohr's law and we're exploring precision in the lab. Okay, so we're going to be dealing with a lot of data and we're trying to look at precision in that data. And of course, Bohr's law comes underneath or under the properties of gases. So we're told the purpose of this experiment is to observe and measure changes in the volume of a gas sample as external pressure is being varied, right? It's made different. So we're going to be looking at three main things. We're going to be measuring the change in volume of a gas sample after changing the applied pressure. We're going to be predicting the change in volume of a gas sample after change in applied pressure. And then finally, because we're going to have a lot of data, we will calculate precision or standard deviation of collected data and interpret the results, okay? So the idea here is when it comes to precision, remember, precision has to do with repeatability, right? So we have precision, and this has to do with repeatability of data. So if you measure data and you get this value here for a measured data, and then you measure it again, and then you get this value here, then you measure again, you get the value here, you measure it again, and at some point it almost appears that your data is overlapping. We call that high precision, right? High precision, because it looks like whatever you're doing, you're able to repeat this over and over and over again. So we have high repeatability, okay? So it's kind of like that whole bullseye analogy, trying to hit that bullseye. If you're able to hit the bullseye over and over again, whatever you're doing, if it's repeatable, then it's very precise. So when it comes to standard deviation, the value of the standard deviation will actually end up being low. So it's low because the data points, the additional data points are not deviating that much from the original, okay? And then when you have low precision, the data points that you're measuring are all over the place, okay? There's not much correlation. And in that case, we expect the standard deviation to be high. So I'm going to try to continue with this right here. I'm not going to look at the equipment because we're not actually doing this in the lab, right? We're going to get data from them. So let me go ahead and move on. The background, we're told that Bohr's law describes the mathematical relationship between pressure and the volume of a sample of a gas, while temperature and number of moles remain constant. So we're being reminded that in Bohr's law, we are looking at the volume and the pressure of the gas, right? To quickly recap, we saw before, the volume is inversely proportional to the pressure, like that. And for that reason, when you replace proportionality sign with an equal sign, we get volume equal constant, and then you multiply by 1 over pressure. You essentially replace the proportionality sign with the equal constant sign. So this replaces that, okay? So at some point you see, well, actually they use K in the place of C. So that was K. So we can paraphrase this by rearranging the equation and saying pressure times volume equal constant. And that's the expression they have here, saying that Bohr's law may also be expressed as pressure and volume equal constant, where K is the proportionality constant, right? Meaning that you have different external pressures and you're able to see how the volume of the gas changes in response. So once you have that external pressure measured and the volume, the new volume also measured, the product of the two will be a constant number. So I am assuming at some point in the lab, we're going to be showing this. Okay, so let me go ahead. Students will test Bohr's law using a simple syringe apparatus that allows for a quick measurement of a sample of air, measuring changes in volume as the pressure on the sample of air is changed. Because the sample of air is sealed inside the syringe, for us to observe the inverse relationship, number of moles and temperature has to be held constant. Okay, so that's very important. Okay, temperature will be measured pre and post to assess whether the temperature was constant or not. If it's not constant, all your data is useless, right? This law is only observed when number of moles and temperature are kept constant. Hold on a second, let me adjust my position. I remember my husband told me, you don't have to be so close to the mics. I'm going to move away a little bit and be comfortable. Okay, Various weights will be hung from the syringe apparatus, applying an increase in pressure on the air sample with a resulting decrease in volume, because we know they have an inverse relationship, right? When the pressure goes up, the volume goes down, and vice versa. Air is regarded as the ideal gas, or as an ideal gas for this experiment. So, oh, by the way, these laws that we saw, the simple gas laws and the ideal gas laws, tend to apply to ideal gas laws. When the gases are not ideal, we start to see, or we start to observe, deviations from the gas law. Okay, I'm trying not to talk too much outside of what's written here. Okay, I do like the little blurb they have here, so I'm going to go through and read this. In previous laboratory activities, students learn to measure accuracy, which is how well one measurement agrees with a known standard value, and how to calculate percent error. In this lab, I'm going to add here, however, students will focus on how to evaluate a group of measurements when there's no known or standard value with which to compare. For example, if several students measure one student's height in centimeters, they will most likely have a variety of measurements. Well, which measurement is right? Because there is no standard value of the person's height. I would say there kind of is. The driver's license, but we tell them what our height is. So technically, that's not really a standard, right? You measure it at some point. So yes, there is no standard value for the person's height. The agreement of the group of measures is determined instead. We're trying to figure out, say for example, this is me, right? And y'all measure my height and you find that I'm 5'5", 5 feet, 5 inches. And let's say out of 10 people, 6 people agree this is my height, then guess what? There's a very high likelihood this is my height, because more people than not in the group are getting that height. Does that make sense? So that's what they mean by that. That when you don't have a standard value to compare your data with, then you have to compare the data taken with other data taken, okay? And that's what precision is, how one data taken compares to another data taken, or a set of data taken. So hopefully this is clear and I'm not confusing you guys any further. Let me delete all these drawings, clear all my drawings, great. Okay, let's continue from here. The measure of agreement is known as precision and is measured by performing a standard deviation calculation. It is typically necessary to have a minimum of 10 measurements in order to evaluate precision. Okay. Interesting enough, in our on-campus lab, that when we do something like this, very similar to this, we don't have 10 measurements. We end up having 6 at most if we have 6 groups. But yeah, it is, if you want to get better quality deviations or better quality sample size, you want to have at least 10, okay? Therefore, each student will perform 10 separate measurements of pressure and volume in today's experiment. And when we say perform, we will get that much data, right? Okay, let's go ahead and move on. So let's see. Let me get out of here so I can scroll down. It says here, you will use a syringe as a container for your ideal gas sample. In the first part of the lab, you will increase the pressure inside the syringe, pressure total. So here's where I want to write this. So PT is the pressure of gas, because that's the pressure inside the syringe, okay? So I'll say PT is the same thing as the pressure of the gas. That's the first thing I'm going to write. Okay, and it says here, in the first part of the lab, you will increase the pressure inside the syringe by hanging weights to push the plunger further into the syringe, causing the volume to decrease. The pressure due to the weights is P weights. Okay, so for this part here, no, don't die. For this part here, I'm going to draw a mock picture of the syringe. The syringe looks something like this. Let's say this is a syringe, right? And then you have the part where the needle is right here, and you have a little tube that hangs over here, okay? And there's a seal down here. So instead of you using your thumb to press down on the plunger, right, to push that on the trapped gas here. So here you have the gas, which the gas we said was air. What they're saying here is you're going to hang some weights. And the weights, okay, will hang somewhere here like that. these weights will pull down because they're acting downwards. They will pull down on this and apply a constant pressure, and therefore pushing down on the plunger, and then the plunger will then push down on the gas, and that should decrease the volume. So the pressure due to the weight is called P weight. So you remember from the applying physics here, the pressure applied on the gas, so the gas will experience the pressure from the weight, that will be called P weight. Okay, must be added to the atmospheric pressure. So there is an atmospheric pressure also acting on the gas. That's going to be called PATM, the pressure of the atmosphere. Total pressure is then equal to P atmosphere plus P weight. So they're saying here, the total pressure, which is also the pressure of the gas, right, is equal to P atmosphere plus P weight. Okay, so write it here. Total pressure is P atmosphere plus P weight. And this is the first equation you want to have here. Okay, so what I'm going to do here is I will move this over and show you guys a spreadsheet I created to help me not have too much mental fatigue as I'm going through all the math, because you see they give us a large table. Okay, let me go ahead and hang up from my team so I don't have redundancies. Okay, so now I'm just on Zoom. Anyway, let's continue from here. And that's the first thing we get from this part here, right? How to find PT. In the second part of the lab, you will invert the syringe. Okay, now while I'm here, I want to show you guys the picture that they have. This is a lab. This is the setup right here. And you can see, right? This is your syringe. Here's your plunger. And normally, if you were trying to apply pressure and the gas that's trapped in here is air, if you're trying to apply pressure, you will use your thumb to press down here. The issue we have is it's hard for you as a human to apply consistent pressure. Sometimes you may push down too much or push down too little. So to make it kind of even, they decided to attach this device here, this little loop, where you can hang the weight, and you can see the picture right here. When the loop has weight hanging on it, it's not pulling down, right? Or pushing down. It's pushing down on this plunger right here, and therefore applying an external force on the gas that is trapped in here. And then we're told that we have this rubber part right here. What is it called again? The pigtail. From here to here, this rubber here is called a pigtail. So this right here is holding, well, I guess from here to here, is holding about 1 milliliter of gas, of air. So from here, all the way to here is holding 1 milliliter of air. Okay. Okay, I'm trying to write 1 milliliter of air. Anyway, you get the idea, right? So that will factor in later on. So I feel like I'm getting ahead of myself. But the first half of the lab, this is your setup right here, if you were to work on this in lab. So you're going to adjust the weights on the plunger, adding different weights, adding more weights until you get the measurement. So for every weight you add here, you're increasing the external force, and the goal is for you to measure the volume, right? Okay, so let me go back to, let's see, delete this, clear all my drawings, and I'll go back to where it said the second part, right? In the second part of the lab, you will invert the syringe. In this position, the weight pull the plunger in the opposite direction, decreasing the pressure inside the syringe, thereby increasing the volume. So this time the external pressure is decreasing. I don't know if I can draw this upside down. Let's see. I'm going to have to draw the syringe. Okay, this time the syringe is facing up like that. And you have your needle in here, and then you have the, I want to call it the oxtail. No, the pig's tail right here. Then you have the little clip that prevents any more air from coming out. This is still 1 milliliter here. And then you have your plunger, right? Your plunger is on the bottom this time. And then this time the weight is hanging on this, okay? So here you have the weight, and the weight is pulling the plunger out. So it's actually acting on the opposite direction. So remember, the atmospheric pressure is still acting on this, the air, okay? And the plunger's the weight from the plunger, the weight from the mass is actually acting in the opposite direction. In the first picture, they were acting in the same direction, right? The atmospheric pressure and then the pressure from the weight. Here, they're acting in the opposite direction. So before I get ahead of myself, let me read what it says here. In this position, the weights pull the plunger in the opposite direction, therefore decreasing the pressure inside the syringe, thereby increasing the volume. The pressure due to the weights counteracts some of the atmospheric pressure. For that reason, PT, pressure total, which is actually the pressure of the gas, is now due to the pressure difference, with the pressure of the atmosphere being the higher one, right? So the pressure of the atmosphere minus the pressure of the weights. So these equations are important in the work you're going to be doing later on. Okay, so I'm writing them down here so we can make sure we're seeing them in an uncluttered space, because they're pretty much saying it here, but I want to make sure you guys can see it. So we have pressure, atmosphere. For the first half of the experiment, that's the equation you use for PT. Second half of the experiment, that's the equation you use for the PT. Okay. Beginning by measuring today's atmospheric pressure using your appropriate weather app. We don't have a weather app. Atmospheric pressure is typically reported in inches of mercury. Now, in the lab, we tend to use millimeters of mercury, and that's why, remember, in lecture, we say 1 atmosphere is 760 millimeters of mercury, but we also talked about this in lecture, right? 1 atmosphere is 29.92 inches of mercury, okay? So they're saying here atmospheric pressure is typically reported in inches of mercury. You will need to convert the value to pascals. The work we're doing today, we need pressure in pascals. So we learned this in lecture also, that 1 atmosphere is equal to 101,325 pascals, okay? So use definitions to make the conversions. Okay, so we're given all these definitions here. I'm not going to be doing all of this right here, okay? Record the atmospheric pressure in inches of mercury and in Pascal units in the spaces provided near the top of the report sheet. Okay, so we'll get to that. Record the temperature of the room to the nearest 0.1 degrees Celsius. Okay, so that's 1 decimal place. We'll get to that part. Oh, hold on. Let me get back to my app. What is it? Okay. So now this is the first part of the experiment. And then once again, they're showing you what's happening here. And this is a close-up showing you the plunger position at 5 milliliter and the open clamp. This is before the experiment starts. And then when the experiment starts, of course, they put a weight on here, right, to pull down on the plunger. Okay. So I'm not going to be reading through all this stuff. I just wanted to show you guys when they flip this over what that looks like. So here the syringe has been flipped over. It's kind of hard to see. I don't want to move stuff too much, but the syringe has been flipped over. You can see right here. Here is the pig's tail right there. Okay. Can I make that bigger? Okay, let me see if I can make this bigger. Oh. Okay, yeah, that's a little bigger right there. So y'all see that, right? So this is when it's flipped over. The syringe has been flipped over. And so this metal thing here that's holding onto the plunger, it's kind of attached to the plunger via a rubber band. There's a rubber band here holding into the plunger. Is now actually gently pulling on the plunger and causing the space where the gas is contained to expand, right? So the volume gets bigger, and it's showing you this up close. Because in the beginning, I think we started off with 5 milliliters, right? Now you can see here, after the weight got added, the space got bigger. Now we are around 10, okay? But the idea is, in this case here, the way you figure out the pressure of the gas is different, because now you have competing pressures, while in the first half of the experiment, you had pressures that were reinforcing each other. Anyway, sorry. The wire I have from my iPad keeps moving stuff around. Anyway, it says be cautious here. Well, we're not going to do much with this, because once again, we are actually going to get data from them, right? I just want to write down important conversions here. When we're calculating values, I want to write this in the clear page. For pressure, we'll use, for the pressure of the gas, it says here, calculating PV values. Let me zoom out so we can see the words, right? Okay. In calculating the PV values, we're told for the next, for each measurement, you will need to calculate the pressure that results from the addition of the weights, added mass, hanging on the syringe. P weights. Pressure, P, is defined by force divided by area. So this is the pressure that we're trying to measure, right? P weights. This is equal to the force applied over the unit area, okay? So this is an equation that we actually mentioned in lecture, but we don't do much with it. But here in this lab, we're actually doing something with it. Okay, it says the area of the plunger is calculated by using the equation of a circle. So I'll say here, we use the equation because we're doing area, not a volume, right? So it looks more cylindrical to me. So our area here will be pi r squared. So you take pi, and then they measured the radius of the syringe. The radius is, well, we're given a diameter, right? That's right here. The diameter is 15.00 millimeters, right? 15.00 millimeters. And the diameter is that. But we want the radius. So the radius tends to be the diameter divided by 2, right? So while they were converting the diameter to radius, they also converted the units. So we're just gonna copy it. So from here, we get that the radius is equal to 0.0075 meters, okay? We need the radius in meters. So now that we have that, our area is calculated by pi 0.0075 meters, and then you square this, okay? So they do that work for you over here. So our area inside the syringe is 1.774 actually times 10 power negative 4 meters squared. So we have this part here done. What about the force? We're told here, by the way, we didn't use this formula in general chemistry, but this formula is true, and we kind of have to go to physics for that we're told that the force is equal to mass times acceleration. This is an equation, okay? And since our mass that we're looking at is a hanging weight, the mass, let me see if I can go back to the image. This mass right here is actually acting downwards because gravity is pulling down on it, okay? So since gravity is pulling down on it, the acceleration of the mass will match acceleration due to gravity. So our A stands for acceleration, by the way. Yeah, this is mass. And this A here is acceleration. But since we have a hanging mass, our acceleration is the same thing as the acceleration due to gravity, which has the symbol G. Okay? So here, F equal ma. So A is the same thing as G, acceleration due to gravity. That's equal to 9.81 meters per second squared. This is a constant that is figured out through experimentation. So don't try to figure out where this is from, okay? Okay, with that being the case, then, once you have the mass, by the way, for this to work, the mass has to be in kilograms. Oops. The mass has to be in kilograms. The acceleration has to be in meters per second squared. That way, when you multiply the units, you get kilograms times meters per second squared. In the world of physics, and in chemistry too, when you're dealing with this equation here, this is equal to newtons. Okay, so 1 kilogram meters per second squared is the same thing as 1 newton. And if you've had physics, you've seen this equality. Okay, and then we're seeing here. So if you're wondering, why do we have to convert the pressure to pascals? The reason why we're doing that is because it says right here, 1 pascal is equal to 1 newton per meter squared, because we're trying to reconcile these units, right? And that's why. So we've kind of gone off track. Bringing this all together, the pressure that the syringe is experiencing from the weight will be calculated this way. Now that we know what is what, we'll take the mass of the weight, make sure it's in kilograms, right? And then multiply that by the acceleration due to gravity, which is 9.81 kilogram. No, no, kilogram, sorry, meters per second squared. Meters per second squared, right? Divided by the area, which we figured out what the area was, which is this one right here. So I'm just going to put in the actual numbers. 1.774 times 10 power negative 4 meters squared. So what we need to do now to find the pressure of the weight is just to measure the weight, convert it from grams to kilograms. Once we have that, then we can figure out the pressure of the weight. Okay. So I'm showing you what all these formulas are. Okay, so let me put a box around the formula so we can see what we're going to be using later on. Can I highlight these? No, this is for writing. Let me try to highlight these so we can see. Just so when we see, okay, this is important to note. The area here is important to note. This equality is important to note. Okay. This equation right here is important to note. So I'm putting a box around all the things we're going to be needing later on, okay? When we go to the lab page, you see how this plays out. Okay, so now let me go back to where I was and then we'll continue. Okay, for each measurement, calculate P waste and PT, remembering to either add or subtract P waste as appropriate for the syringe setup using each experiment. Finally, calculate your PV values. Remember that the units for PV value in report table BY.1 are Pascal times milliliters. Record your calculations of PV rounded to two significant figures using scientific notation. Okay, so this is a lot of requirements, right? So we're told here, eventually when you find the pressure, oops, wrong. The pressure will be some number with the unit Pascal, right? And then you're going to get volume, some number here with the unit milliliter. You're going to have a column where you calculate pressure times volume. Remember we said, well, Boyle's law, pressure times volume is equal to constant. Now, our constant does have a unit because pressure is pascals, volume is milliliters. So our unit will be pascals times milliliters, okay? We're told to record the PV value. We have to round this up to two significant figures. I'm writing this down so I don't forget, right? And then I have to use scientific notation for the PV value. Okay. Part of the lab is also to do standard deviation. So what do all these PV measurements mean? To evaluate a group of measurements that have no known standard value, such as what we're going to have above, we want to calculate precision, which is the agreement or lack thereof amongst the successive measurements in a set. Finding the standard deviation. The lower the standard deviation, the better agreement you have amongst your measurements. So what is the formula for standard deviation? We have it right here. Standard deviation or agreeability is equal to the square root of, this stands for the sum of the deviations squared over n is the number of samples or sample size minus 1. So D is your deviation. How do we get that? Take the pressure times volume, this constant right here, and subtract from it the pressure times volume, that's the average. So in other words, we're going to have a bunch of pressure and volumes, right? You will add those up, get an average, and then that will go right here. So they say AVE for average. And then N is the number of sample size. How many times did we do that experiment? Number of experiments, which they call this the number of measurements made. So I'll say number of measurements. Let me be consistent. Measurements. That's measurements. Measurements. Okay. I was being lazy. Okay, so it says start by calculating the average of all 11 PV calculations from report table BY1 and entering PV average in the report sheet in the standard deviation calculation section. And then let's see right here. Okay, so what I'm going to do here is it says complete by subtracting the mean PV from the measured PE and then squaring the result. And then sum the D squared values and record this answer on the sheet. Okay, so I'm going to be doing all this, right? And then it gives you an example of how to find it. Divide the sum of the D squared values by the number of measurements made. In our lab, you will see we have 11 measurements. So that means N will be equal to 11. And therefore, N minus 1 will be 10, right? And then record the standard deviation on the report sheet. And then they want us to, it says, to obtain the standard deviation, take the square root of standard deviation squared and record this on your answer sheet. Finish by writing the range of values, of PV values that fall within the plus or minus 1 standard deviation. The low number of the range is the mean minus your standard deviation value. The high number is the mean plus the standard deviation value. Okay, so just to kind of give you a snapshot of what they're saying here, say your average was 5, okay, and our standard deviation was 1. You're saying that your average, which is 5, plus or minus the standard deviation, which is 1, right? So I'm going to erase this and say this is 1. That means our range of trusted values will be between 4 and 6. Okay, you take 5 minus 1, you get 4. 5 plus 1, you get 6. Okay, so this is just telling you that the correct data lies within this range. Everything outside of this range is sus. Okay, because remember, when you're making a lot of measurements, some are going to be wrong, some are going to be right, some are going to be more right. But we have this range right here telling us the range of correctness. Anything outside of that range is wrong. Okay. Okay, I feel like I've done enough. Let's go ahead and actually get to the experiment. I do all this here so I don't have to come back here, okay? You will see there's a lot of data. Confirm. Okay. Okay, so what I'm going to do here for now, I copied all these equations here. I'm going to scoot this down. This is my bestie. Yeah, I'm going to scoot this down here. And what I'm going to do right now is I'm going to scoot this down here. I don't need that one either. I actually need the Excel spreadsheet. Okay, so I prepared this Excel spreadsheet here because it's a lot of numbers, y'all. A lot of numbers. And it's hard to write the formulas so they look really good, but I'm going to try to make this Excel spreadsheet look like the one we have. So I don't have to calculate each and every one of these data sets because it's a lot. Okay. So here, let's see. We have reading 1 all the way to reading 11. And then here we have the different masses. Okay. So, oh, I see. My Excel spreadsheet was trying to copy the second one here. So you see, we have the masses added that corresponds with that. So let me go ahead and copy this mass added here. So this is going to be what? 0 0.0, 0 0.1. So you see, I'm inputting the masses, right? 0.35, 0.500. By the way, if you want to know how I got this to have the right decimal places, there's a menu over here. Okay, I don't know where it is now. It's somewhere here in the past. Oh yeah, this one here. So for this part here, right, you can select that. You can go like that and it adds a decimal place, or go like that and it reduces. It takes it away. So adding, taking it away. Anyway, just wanted to show you guys that part. And I just went ahead here and type in the reading 1, 2, 3, 4, 5. I don't want to type all of it because you'd be bored sitting there watching me type. I type so slow. But my goal, right, once again, is to replicate the second table, right? Oops, I went too far. This second table here. But let me start by inputting the numbers I need. So for the weight in kilograms, I'm at 0.500, 0.800, 1.2. Oh, by the way, if you're wondering why we have two colors, because I was trying to visually not get confused, right? Y'all know I get very distracted, right? So I chose two colors. It's the summer, so I was feeling this color right now. So the top part is the first half of the experiment where the syringe is pointing downwards, right? And that will be, oh, this should be part of that color too, right? Yeah, where the syringe is pointing downwards. The second part of the experiment, the green part, the syringe is pointing upwards. So let me see if I can get this nice color here. That applies to this part here. That applies to this. And so, yeah, so the purple part is syringe pointing downwards. The green part is a syringe pointing upwards, just in case you're wondering. Yeah, it took me a while to kind of type this in, but I got it. It makes my math easier, okay? So I'm at, let's see, after 1, I'm at 0.2, right? And then 0.4, 0.5, 0.7, 0.85. Okay. So we got all this here. What I'm going to do right now is I don't want to mess this up, so I'm going to save it, right? This is saved to my desktop, it says right here. Okay, next, we need syringe volume. So syringe volume of syringe, that's what we have right here. So I'm going to put here, this is 5. And I already set this up to 1 decimal place, so 4.7, 4.4, 4.2, 3.7. So you can see the volume decreases, right? Consistently as the pressure or the mass. The pressure is kind of tied to the mass. As the mass increases, the volume decreases. Then finally, we go down to 3.4. Then we have 5.5, 6.6, 7.2. Ooh. My concern with me being by myself here is me making transcription errors and not noticing it. 9.3. Okay, let me make sure I copy the right numbers. So for this one here, it's 5.0, 4.7, 4.4, 4.2, 3.7, 3.4, 5.5, 6.6, 7.2, 8.4, 9.3. Okay, done. And then we have a temperature here of 20.6. Okay. Oh, at end of measurements, the beginning was 20.6 also, so the temperature remained constant. And then for our masses, 0, 0.1, 0.35, 0.5, 0.8, 1, 0.2, 0.4, 0.5, 0.7, 0.85. Okay, whew, I got it. Let me save this also. Okay, we got our temperature. So that's important. And then over here, let's see, I have all these present. I have the pressure of the atmosphere, right? Enter the atmospheric pressure in inches of mercury. So they gave us the atmospheric pressure. It's given to us here as 30.08. So I'm going to put that here, inches of mercury. Okay. Once again, I'm putting this here because I don't want to have to calculate every one of these. I'm being a little lazy, and I'm using Excel to my benefit to help me not to do the calculation over and over again. I'll set it up for one and then drag it through the column, and y'all see how I do it. So this number here goes 30.08 inches, IN, inches. Where's IN of mercury, Hg. And we have the same thing over here, right? And so I have my conversions here, and you can see when you multiply this out. Since I'm here, I'm going to go ahead and work it out so I can get my number. Okay, so I think it's the same mass. Let's see. I'm doing this on my calculator. 30.08 times these conversions of what I gave you earlier. 101. Let me move this over. 325 divided by 29.92. And I'm getting 101.867 pascals. So this is done, right? I'm going to highlight this. I need that for later on. I'm going to highlight it yellow. Okay, so I need that for later on. Okay, where are we at? Let me put this in the middle somewhere here. Yeah. Okay, so back to this one here. We have taken in these numbers. Now I'm down here. So I'm going to do the math here so I can put the numbers in here. So back to this. I think somewhere here in our lab, where is the lab? Let me find it. It mentions something about the pigtail having 1 milliliter. I just want to make sure that I show it to you because I read this earlier. Oh, right there. Remembering to when you're recording the volume, it says here, remembering to add 1 milliliter for the volume in the pigtail. The pigtail is that rubber, like the rubber hose at the end of the syringe or where the needle goes into, or the tip of the syringe goes into. And so whatever volume you have measured or they give us, we have to add 1 milliliter for the volume to account for the volume of the gas in that pigtail. So it says so right here. Okay. Yeah, this one here, this is where you have the 1 milliliter. So it tells you here, with the clamp at the bottom of the syringe, open, adjust the syringe plunger to the bottom of the black rubber. This is when you're starting the experiment, is at 5 milliliters. That's why when you look at the volume here, where's the volume? The volume in the beginning, right, is 5 milliliter because that's where you start. And it says adjust the position of the clamp so that you estimate the pigtail at the bottom of the syringe contains approximately 1 milliliter of air. Okay. So you see why I bring this up, because over here we have to find the volume total. So the volume total is the volume we have plus 1 milliliter. And I put this up here so y'all don't forget, right? That's how we get this. So the volume of the syringe plus 1 milliliter. So it's going to be 5.7. I struggle to do the head math. 5.4, 5.2, 4.7, 4.4, 6.5. Because there's a thinking, there's a typing, right? 7.6, 8.2. Oh, you know what? I said, oh my goodness, I am such a, okay, you know what? Because I'm not sure if I did this right. Let me just go ahead and do the whole point of me being here is doing this, okay? So instead of I'm typing everything out, and I told you guys I didn't want to do that. Okay, so this is equal to, I put equal to, that's my equation, my formula, right? Equal to, oops, wrong place. Equal to, I want this, right? That number, I want to add 1 to it. I forgot why I was doing this on Excel. So this is the first one, right? You see this 5 plus 1. Now just go ahead and pull this down here. And that should adjust everything else. That's it. See? So it does all of this for me. When I click on here, it says we took B2. So B is this column here. 2 is 5. And we added 1 to it. You do it down here, same thing. We took B6. B6 is this one. Added 1 to it. Same thing with that. See? The whole thing is done. What was I doing? I forgot. Okay, so with that here, let me go ahead and copy this number over. Because the goal, 6. 5.7. Yeah, I should spend my energy here instead. 5.4, because there is no Excel spreadsheet here. 5.2. 4.7. 4.4. 6.5. 6.6. This is 1 more, 1 more. Oops, see? This is why I check, because it doesn't take much for me to forget. 7.6, because I'm not really looking at this. 8.2, right? 9.4, and then 10.3. So let me double check. First one should be 6, 5.7, 5.4, 5.2, 4.7, 4.4, 6.5, 7.6, 8.2, 9.4, 10.3. Okay, that's done. This column here, this is asking for force. Now we had our equation somewhere here where we said force was equal to mass times acceleration, right? How do I get this back here? force was equal to mass and acceleration. Yeah, there. So since we have the mass in kilograms, all we have to do is multiply by acceleration. So we should be good, right? And it has the units here, kilogram, meter per second squared. Okay, so did I put the formula here? Yes. Oh, I didn't really put the acceleration. So force is equal to mass times this number. This is the acceleration. So for that, what is my mass? Instead of typing each one of these in the calculator, I'll just put an equation here. So I'll start by putting my mouse here, clicking, doing a left click, because right click does this, right? Right click gives me a menu, left click on the mouse. Then I type equal, and I want this mass here. So I'm going to click on this, so it selects D2. To be multiplied, I put this, what's that sign? That's not really a hashtag. Whatever, that multiply, right? By 9.81. And that will give us the force in kilograms times meters per second squared. Okay? Since the first mass is 0, this should be 0. But when you drag this down, it multiplies all of these for you. Okay? So according to this is the correct force. Okay? So I'm going to copy that here. 0.00. No. I'm not submitting. 0.0. I forgot you can't press enter here. Okay. And this is going to be 0.98. .43. So I'm copying this one here, right? So 0.0.983.43. And what's next is 4.91. You can see the old numbers I worked with, 4.91. And next, I got 7.85, right? Just to double check, is this, yes, this is whatever D6 is, this number times 9.81. I like to double check just to make sure. 7.85, and then what comes next is 9.81, 9.81. I wish I could just import this, right? Then here, this is 1.96. Oh, that's the same number, 1.96. Then here we get 3.92, 3.92. And then 4.91. 6, oops, I said 6 and typing 1. 6.87. I have to be really careful here. 8.34. Okay. So once again, I'm copying this column right here because this column goes with force, right? So let me make sure 0.98, 3.43, 4.91, 7.85, 9.81, 1.96, 3.92, 4.91, 6.87, 8.34. Okay, that column is done. The next part we're looking at here is P weight equal P syringe. Oh, okay. I wrote that here because in the text, right, in your lab, they refer to P weight, and they refer to P weight as the pressure from this weight. And I was like, great, I like that label. P weight is so, it makes sense. And we said pressure total is P atmosphere minus P weight for the second part of the experiment, right? For the first part, PT, pressure total, is P atmosphere plus P weight. So here's the thing. When they get to the table, there's no word, there's no P weight label. There's P syringe. Come to find out, P weight is P syringe. I'm like, come on, people. These are the kind of things where I write things down. You have to really pay attention because chemists do that. It's a bad habit where they switch. I'm not the only one with focus issues, but you have to be attentive or else you get lost and you're thinking it's you and it's not you. Okay, remember I mentioned before that the pressure is force over area, and it's somewhere here in the many things we have on here, right? Pressure is force over area, and we're looking at P weight, which is now P syringe. We already have the area. The area is a fixed amount because it's just, the area is just the area of the syringe, right? So that's that amount there. And then, yeah, we assume it's fixed, and we're looking at the pressure. and the pressure is going to be force, and the force is mass times acceleration. We already have that one, and then divide this by area. So since we already have force, all we need is area, which I already copied the number here, right? So we take force divided by area. And I put this here so I don't have to remember the formula so much. Y'all, I work hard so I can be lazy. Because before I was like, I don't have to think too much and go back there and think. Because every time I click the page and I move on to something else, I forget what I was doing. I mean, it's not that bad, but y'all know how I struggle with focus issues. Okay, so where was I? Right here. So I don't need this one here. Okay, we're looking at pressure of the syringe, which is the same thing as force over area. The force is over here, the area is over here. So I have to put in the formula again. Equal to, I need the force. This is the force, right? So I take this one here, E2, and divide this by backslash. That's backslash? Yeah, that slash. Divide by, I'm going to put open parentheses because I want the calculator in Excel to see this as one number. 1.774. And then I'm going to use this because this means multiply 10, right? And then shift hat. So the hat can show up, power. I'm going to open parentheses here. Ooh, shift, and then 9, so I can open parentheses. So I'm going to be using -4, and I wanted to recognize the number as -4, so I'm parenthesizing it so it can recognize the number, right? Since I have an open parentheses here, I have to close it here again, so I'm going to close the parentheses. Bam, like that. Okay. When I do it right, I get 0 because remember, our first number here is 0. Okay, let's drag this down and see what happens. Yay, we get the actual numbers. Okay, so this is the pressure that we have right now. And the pressure here has what unit? Oh, pascals is right here. You're moving on now to, I have to copy this over, right? It's going to be 0. This is going to be 5530. This is different from the first one I did. I got 19355, right, for the second one. I got 27649. That's the fourth one. So the first one is 0, 5530, second one, 19355, third one, 27649, fourth one. Okay, 44239. So I'm back. So let's double check because I was kind of zoning out a little bit. 5530, 19355, 27649, 44239. And here I got 55299, right? Then I got 11060, 22120, 27649. Then we got 38709. I usually zone out when I'm copying numbers, 47004, because to me it's very boring, right? Okay, we made it through those numbers, but the colors here are not consistent with my, so let me go ahead and zoom this out a little bit and then get the right color here. This is supposed to be green, not that green, a lighter green. Yeah, okay, better. Okay, so here we have 2 columns left, right? PT, we know the first half of the experiment, the PT is different, right? Okay, so let's look at this over here. Oh, yeah, I don't want them to be a distraction. Okay, let me move this over if I need this right now. Oh, well, you know what? I did write these here, right? So we have that there. This is that. So PT, we know that PT for the first half over here, we said PT was what? No, that was the first half. PT was equal to P atmosphere plus P weight. Okay. Second half is P atmosphere minus P weight. So for this one here, it's going to be tricky, right? I have to say equal to, where's P atmosphere? Oh, we need this in pascals, right? P atmosphere was 30.08, this one here, but I converted it over here into pascals. So let me write this down somewhere. It's 101867. Okay, I wrote it down. So I need that one. Okay, so I'm going to write here PT. I have the formula, but it's not consistent. So in the first half, it's P, the first half of the experiment, right? Hold on. Let me set up the first half first. The first half is P atmosphere plus P weight. So we have P weight is the same thing as this one here, right? So I'm going to put P atmosphere here. I have 101. So of course I make it equal again, 101, 867. Okay. So I'm going to take P atmosphere, add it to P weight, and P weight is P syringe. So shift plus this number right here, and then press equal. Okay. And then drag this down all the way to here, because it really only applies for the top half, right? And then on the bottom half, we do the opposite, make this equal, and then this time they said what? Take P atmosphere, subtract P weight. So P atmosphere, once again, 101, 867. Subtract this. And you only do it once. Don't drag the whole thing, just the one number, because you want to get that equation to be right. Correct? And then, is that what I'm doing? Yes. And then drag this down. P atmosphere minus P weight. I have this written here. Right. So yeah, this is where I will be needing. Okay, so we got, oh, the number came out the same? 101,867. Oh, because, okay. This is 107,397. These numbers are a lot. So if I mess up, I'm going to give myself some grace. Okay, so let me move this over so I can see what I'm writing. Okay, 101,867, 107,397, 121,222, 129,516, 146,106, 157, 166. Okay. So quick check: 101,867, 107,397, 121,222, 121,222, 129,516, 146,106, 157,166. Okay. Ooh, I thought I messed up for a moment there. 908,07. 79747, 74218, 63158, 54863. Okay, let me check the green part. 90807, 79747, 74218, 63158, 54863. Okay. Now this last column has us taking pressure times volume. So we're going to take pressure times volume, okay? This color should be here. And it doesn't matter. Okay, so for pressure times volume, I'm taking this pressure, right? The total pressure. And I'm multiplying it to the volume all the way over here, this total volume. So it'd be C2, okay? So I'm going to take this as equal to this pressure, G2, multiplied by, scroll down here, V2, the total pressure. And then don't click anywhere else because it will select that 2, right? And then just press enter. And there it is. So we have this number right here. So we want to do the same thing for all the other numbers in the column. Not bad. Remember PV is supposed to be constant for Boyle's law, right? So you see that right there? Okay. So I'm going to write here. Oh, this is what they were telling us to write two significant figures, right? Let me see if I can move this over. So I'm going to write here 6.1. Yeah, that works out. Let's see, the decimal 1, 2, 3, 4, 5. Yeah. So two significant figures, 6.1. So I have here 6.1. I'm going to be lazy and copy this number over and just adjust this number over and over again. So I'm going to copy that number right here and adjust it. Okay. So 6.1, this is still 6.1, right? Because you move this 1, 2, 3, 4, 5. So 6.1 times 10 power 5. This would be here 6.5 times 10 power 5, right? 6.5 times 10 power 5. 1, 2, 3, 4, 5. Yeah. And this one here would be 6.7. So no, I'll make this 7. 6.7 times 10 power 5. Okay. That's why it helps to have the colors, right? Let me go ahead and color this so I'm not getting lost, because these are huge numbers. And for me, I'm doing a lot mentally right now. And so I want to make sure I'm not checking out low key, because my brain can if something is a little bit boring for me, my brain can be like, I'm just gonna bounce. I'm gonna be on a power save mode because this is not really so stimulating. I know. It's not challenging, it's not stimulating, so I'm just gonna go in power save mode. Okay, so here I'm at, so at 6.1, 6.1, 6.5, right? 6.7, 6.9, 6.9. I got it. Now the second half, 5.9. So I'm going to see. I'm just going to paste this. Let me just paste this all the way to the end because it makes my life easier just to paste that. And I'll adjust the first number because it looks like they all have the same decimal places. Okay. So this is going to be what? 5.9. So I'm going to type here 5.9, delete. Okay. That was this one here. And this is 6.1, so I'll leave that as is. This is 6.1. Also, I'll leave that as is. This is 5.9. 5.9 times 10 power 5. And then here we have 5.7, right? You see how the P times V came out constant? Like roughly constant, even though our numbers were kind of all over the place. 5.7. Okay. So this is where we're at. So this table, oh my goodness, it's finally done. This one table, right? And you see that, right? Most of the work I did was right here on Excel spreadsheet. So I wasn't manually typing everything. Okay. Now that we have all these numbers here, which are pretty, I would say they have good precision, but we don't know. I'm just making a judgment, right? I'm speculating because I really don't have numbers. It says calculate the mean value. That's the average of the PV column in the table above. So this column here, they want the average. Now, naturally, I'll take this right here and plugging all these numbers in the calculator. But y'all see my brain is already checking out. I'm already mentally fatigued. So let me go ahead and use this system here. Press equal, and they want the average, right? Which is like the mean. But let me see. I don't know if mean is a thing here. No, it's not. So I'm going to use average equal AVE. Oh, they have average. Okay, so I'm going to say average. Then they show open parentheses. Use your mouse, the left key, click left on the mouse to select that. Then drag all this one here while you're holding the mouse down, the left clicker. You know what I mean? The left button, hold it down, drag this all the way down, just vertically to select all of these. If you can't do that, then another thing you can do, let me show you how to do that, is press equal once again. Type in it will show up average, select that. The open parenthesis shows up. You can start with this first one. This first one is what? H2. You can type in here H2 and it will highlight that. And then you want to use colon and then the last one, H12. Yeah. And it selects the whole thing for you. Press enter and then you get that. And that's the average of these, right? It says this is the average of from H2 all the way to H12. When you click on that, it selects all the numbers, right? Okay. So that's our average. So I'm going to put this right here. I'm going to write it as, I can write the whole number, 6266669. 6266669. That's the average. Okay. Copy each PV value from table 2 into table 3. There's no place for PV value. So why are they giving us directions and there's no place for us to write it? Because you see, this is not the PV value. So do not do this. Do not do this. There's a missing column here for us to put in the PV. So I just keep going back and reading this, right? Copy each PV value from table 2 into table 3 below. Next, for each measured PV value, subtract the mean PV value you just calculated, square the result. Okay, we do have the deviation here, but we don't have a column or space for us to type in the PV values from above, which is great. It's less work for us. Okay, so deviation is equal to PV minus the mean. And I told you guys this earlier over here, right? Oh, there, right. So to find D, you take the PV from the column minus the average PV. So let's go ahead and do that. Let's just do the deviation first. PV, which is what's in the column here, minus the mean. Okay, so I already have PV here, right? So I'm going to find the deviation D, which is this formula here, equal to this number minus, I will write the actual number. Okay, let me type the actual number. The actual number is 626,669. Okay, 626,669. Let me try that and see. Okay, first one works. Let me try it and see if the second one works. Okay, 626,699. Okay, let's keep going. Try all the way down here. Okay, 626,699. I'm looking at the second one, 626,699. 669. Okay, 626,669. 626,669. Okay. I think I got it this time. Okay. Woo! Third time is a charm. Okay. So I got my deviation here. Now I'm going to copy this number over here. Ooh, this lab, you got to really focus. You got to really focus. The good thing about this lab is you can start and stop, right? So I want to get this done. Negative 154,154,67. That's the first number. Second number, negative 145,06,07. Let me change this to 0 decimal places because the numbers are a lot. Where is that? It's saying show up. Let me drag this out. Hold on. I don't have to round up and down in my head because when I do that, it just adds more mental fatigue. Okay, so the first one is negative 154,67, negative 145,07. Okay, 279,279,27. Okay, 468,16, 60029. When you're working on this, you can get to a stopping point and then come back later, right? Just figure out, remember at what point in the video you stopped and then come back to that. I can't, I have to keep going. So 64860. Okay, let me check my numbers before I go to the pink section. 15467 negative. 14507 negative. 27927. 46816. 60029. 64860. Okay. Negative 36422. Negative 20588. Negative 18085. Negative 329. Oh, I said, oh, these are all negative. I forgot negatives. Man, I was thinking about something else I do in school that has to do with this. I'm trying to make sure. Okay, negative. Yo, I said negative. I didn't actually type it in here. This is the stuff that will bring in errors. I hope I get most of this right because I would hate to have to do this over again. But anyway, in these labs, you can just correct the parts that you missed, right? So 36422, 20588, 18085, and these are all negative, right? And then 32985, this is a negative 85, right? Then I have negative 61580. Ooh, I made it. One more column. Okay. Then we're told here we should square the deviation. So in this case here, just square this deviation, right? So I'm going to take this equal to, take this number here, and then square it. How do I square this? Shift hat 2, right? Okay. So then let's drag this all the way down here. Oh. Okay. So the deviation doesn't have to be constant, right? It doesn't have to be constant. Oh, let me delete this now because I'm trying to show you how I enter these functions here. So I don't want to have them pre-entered, right? So this, let me make sure this is correct. This is that square, this is squared, this is squared, squared. It didn't do anything crazy. Okay, just the function squared. Okay, let's start here. Okay, so I'm gonna go ahead and start the deviation squared. So for this one here, they want us to write this in two significant figures, right? So I'm gonna start with the first one here being 2.4 for the first one, right? And if you look over here, is imagine a decimal here. You're moving over 1, 2, 3, 4, 5, 6. Wait, over here 1, 2, 3, 4, 5, 6, 7, 8. So 2.4 times 10 power 8. Okay. So this number here occupies the same space as this number and this number. So I'm going to take this number here and copy it over twice. Because I don't feel like typing this. I mean, I could, but I'm already tired here. Okay. Then these two here also occupy about the same space. So I'm going to place that there. Okay. So let's start with the top one. That's 2.4 times 10 power 8. This is going to be 2.1. So I'm going to change this number here. 2.1. Right? And this is 7.8. 7.8. Okay. So that's these numbers here. Let me scroll down to this number here. This is 4.2. No, I was kind of beginning to zone out. It's getting a little bit very mundane here. Then this is 3.3. 3.3. Of course, when I get done, I'll look over everything, right? And then, so the first three are times 10 power 8, right? Then these ones are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So these numbers here that kind of stick out a little bit more, these are all times 10 power 9. So let me paste this one here. And this first one will be power 9. And I'm just going to copy that over the remaining ones, right? And these are, but let me do it section by section so I don't forget numbers. I'll do it section by section. So these middle four here, right, are power 9. So this first one is going to be 2.2. So 2.2, right? This next one here, oops, 2.2, 2.2. That's what this is, 2.2 when you round up. This is going to be 3.6. We're running up to two significant figures. So only the first two numbers from the left are valid. This is 4.2. 4.2. This one here is 1.3 because the first 1.3. 1.3. Okay. So I'm here now. That's that. And these two are these. And then the last two now, I'm going to paste this here. I'm going to paste this here. And so we have 1.1, 1.1, and we have 3.8. Okay, I did better this time around. Let me double check now to make sure. Okay, so here we have 2.4, 2.1, 7.8, and these are all power 8, right? Times 10 power 8. And the next set of 4 is 2.2, 3.6, 4.2, 1.3. And these next set of 4 have times 10 power 9, right? The next two sets are 4.2, 3.3, Yeah, because you round up. And these have a power of 10 power 8. And the last two, 1.1, 3.8, these have a power times 10 power 9. Yay. Okay. So then they want us to add the deviations. So here I'm going to press equal, right? And we want to add. So to add here, you don't use ADD. Is this address? There's no function like that. So you use sum. Then you have to open parentheses because it doesn't just show up. And then select the first one. You can hold this here and then drag all the way down and then press enter. Or if you're not sure, press equal, type SUM, open parentheses, type the first one. Or if you don't want to do that, you can just press, this is K2, the second one, right? K2. That codes to that number K2. Use colon, and then that will be K12. K12. Either one of those will select all of those numbers, close parentheses, press enter, and that will add everything. So over here, we're having 1.82, I think. 1.82. You can type in all these numbers, right? Or you can write this whole number here, 1.82, and then if the decimals here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 10 power 10. These numbers are huge. I really cannot connect with these numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm trying to make sure I did this right. Okay, so the next one says here, now I wrote this out earlier, divide the sum of the square deviation, that's this one here, by the number of measurements, minus 1. So we had 11 measurements, right? Minus 1 will be 10. So take this number here, I'll type here, equal, where's the equal? This, and then divide is this sign here, and then put 10. And so we get the same number, just one less number, right? So it's going to be 1.82. This one here. Let's see. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 power 9. Okay. The next one is square root of the standard deviation. Take the square root of the above number. So this number right here. So for that one here, I'll make it equal to, take this number. What I like to do here is, I can't think of the square root function, so I make it power 1/2. 1 divided by 2, close parentheses. And that's equal to that. Okay. So I'm going to copy that. And that will be 1, 2, 3, 4. It's going to be 4.3. 4.3 times 10 power 1, 2, 3. So we're doing here 1, 2, 3, 4. 4 points. Yeah. 3 times 10 power 4, right? 1, 2, 3, 4. Okay. And make sure 1, 2, 3, 4. Okay. And it says here, the range is the minimum. Oh, sorry. The range is the mean. That was the average. What was it? Where's the mean? Oh, we don't have the average of this number, do we? The range is the mean PV, not this. The mean PV. We have the mean PV. Oh, it's right here, right? The range is the mean PV plus or minus SD. So we have our standard deviation, right? That's it right here. So where's the range? I don't have this right here. Okay, I need to type this in. So minimum range. Min range. I thought I did the math here. Max range. Okay, so for our minimum range, to say the range is the mean PV, that one here, right? The average, plus or minus the standard deviation. Give the range, minimum or maximum, in decimal numbers. In decimal numbers? I feel like I did it somewhere. Okay. In decimal numbers. Okay. So I have to take the average PV. The minimum range is average PV minus standard deviation, right? Let's say PVAVE minus SD. This right here is a standard deviation right here. So the math would be equal to the average minus this number. That's for the minimum one. The maximum one is going to be equal to PV average. PV average plus standard deviation. So it tells you the range of data that's correct. Okay, sorry. This has been a lot. Okay, so it's going to be equal to the average plus standard deviation. Okay, so the correct numbers in the PV value are somewhere between these. If they're not in here, if they're not in this range, they're wrong. Wrong. Okay, so now I can copy this number over. 584020. 584020.16. They wanted it with decimal? Oh, they didn't want it in scientific notation. Okay, I see. 669,317.92. Okay. I hope this is correct, y'all, because this is pretty much it. This is the moment, y'all. So I made it this far, we'll see. I don't even want to look at it over again. I'm just I'm tired. It's been a long. I'm about to say, no, not red. This is the numbers they gave us. Yo, with all the mistakes I made, thank God. So yeah. Y'all saw how I got these numbers. I feel so No, come on. Oh, come on. How is this possible? This is correct and this is not correct. I feel like somewhere in the calculation is an issue because look, so when you square this, you get it. That's correct, but this is not correct. How is that possible? Okay. So you have to come back and check these numbers out because these are PV minus mean. That's what it says over here. And these numbers are correct. What? Okay. So let me double check this from the calculation, right? Because it seems like everything is correct. These are all correct. The issue is these. So I wonder if it's the sign, right? Let's see. So I have to make sure for this one I did PV minus mean. Unless they wanted it in scientific notation, I didn't do that. You know, that could be a thing, huh? Okay, let's see. PV minus the average. So this is the one where I remember I went back in and I typed in the numbers. So it's like PV, this is this number, and that's the average. And I typed this in and I copied it over and over. It's 626,669.04. And did they accept that average? Yes, they did. 626,669. So it's the same number. I'm taking this number here, PV, and it's P average. Let me make sure the formula is correct because you know how sometimes they make errors here. 3716, because 377321. Okay, let me make sure the formula is correct. So for us to get the deviation, it's actually the PV minus the average. So they accepted this average as correct. And this is the PV. So is this minus this? So I don't understand why that's wrong. I think there's something wrong in your setting. No, hear me out. Hear me out. I think there's something wrong in this setting because when I square this, I get the answer correct. What I do with the numbers is correct, but somehow this is not correct. How is that possible? Okay. I was having issues with this earlier when I worked on it too, and I don't know, it was weird. So yes.